Hey everybody, Case Muratori here. This is part 2 of the Refterm lecture. In this part, I go over how to take parts of a codebase that you're not allowed to change and isolate them so they don't cause performance problems, as well as how to not add your own new performance problems by doing things like extraneous copies or forcing there to be more work than is necessary in the initial place where data flows into the system. If you haven't seen the first part, the link's in the description below. I highly recommend checking that out first. And of course, this entire thing is part of our Kickstarter promotion series. It's for our cool graphic novel, Meow the Infinite. We'd love to send you some books, so please check out the Kickstarter link below as well. Without further ado, here is the video, and I'll be back at the end to tell you about part 3. Let me talk about the structure of Refterm, how I kept it non-pessimized, and why I think that it runs so much faster than what you see in a lot of other cases. Now, what happens in a terminal program these days is really very counterintuitive. It's obviously very legacy, and the structure of it is really not able to be changed. So in some senses, even my reference terminal is running probably a good deal slower than it should. And the reason for that is I can only replace so much of the process. I'll talk a little bit more about that later, but I want to draw a quick diagram of it so you can understand what's happening here. So in general, I'm going to draw it going from left to right here. Well, actually, you know what? Let's do right to left, because right to left ordering is something that most terminals don't handle, but Refterm sort of does. Anyway, so if we imagine that we have a program, right? That's running, that's some program that is just a command line program. There's one called splat.exe and splat2.exe that I wrote for use with terminal for testing. So let's say it's something like that. What splat.exe does is really none of our business as a terminal. We just know it's some executable that's running, and we know that it's going to dump a bunch of data, right? It's just dumping data. And that's what a terminal program generally does. It either dumps some data to a file or something, or it dumps some data to the standard output. To the extent that we care how fast a terminal is, what we usually care about is how fast it can sync and display that data. Now, you may wonder why we care how fast it could do that. And some people say we shouldn't care, but I totally disagree, because I like to be able to write terminal programs to do whatever I want. If my terminal program wants to dump 2 gigabytes of data out because it's just some text that's going to go out or whatever, I would like that to just be handled by my terminal. I don't want my terminal to be so slow that I have to go dump it to a file instead, because I know that if I dump it to the terminal, it'll slow down, right, or something like that. So I don't like the idea of my command line programs potentially being slowed down because my terminal is too slow to draw them, right? So what we want to do here is take this output, right, which is generally called standard out, but it could be standard error as well. But the point is, stuff's coming back this way. And unbeknownst to us, I mean, beknownst to us now, but unbeknownst to the user, there's a bunch of garbage that happens in here, right? And this is, potentially multiple things. Where it actually happens, how it actually happens, can change depending on the operating system. But there's going to be at least some kernel and some user space code that's actually put in there by the OS. So splat.exe sends all its data out. That data is first intercepted by the kernel and done something to. We don't know what. There might be user-level stuff on Windows there is, for example, that's going to go looking through it, producing buffers, because there's a back channel here that happens where this thing could be compiled with an API that allows it to ask the operating system for things that it needs to be able to parse this data to understand. So there's actually some nasty crap in here like this that we don't probably really want, but that's just what happens. There's some stuff in Windows 10, by the way, that tries to help you write things to fix this. So that's kind of nice, but ignore that for now. Something like this is going on here. And then finally, after that, it comes out into our actual terminal program. Right? Except, well, does it really? The answer is unfortunately a little bit more complicated than this. It may even be that this is too simplified of a model. It may be that this is actually a shell, right? And Splat is actually running as a process under the shell, and this OS kernel and user are happening again. So this entire process may be the Splat program goes to the OS and the kernel, which goes to the shell, which has to go through the OS, the kernel again, right? And then to our terminal program. Now, why do I bring this up? I only bring it up so that you can understand this whole part of the process, right, is unnecessary. So the part about non-pessimization, we're off on the wrong foot already because none of this should have ever happened, right? All of this is a legacy idea about what a terminal is and what a terminal does. And so we're already going to be, our performance is already going to be capped by how fast this system can get us the data across this pipe. Because it has to do all of these things before it actually ever gets to us. So if the throughput on this pipe, whatever the speed is of this, if that is a certain number of bytes per second, that is the maximum possible throughput that we will ever receive. No matter how fast we make terminal, that's as fast as it goes, right? Now, that's going to come back in later when I talk about the optimization, the little tiny bit of optimization I did on this actual, on Refterm, because the reason that you care and you need to know what this is because optimization is about comparing your performance to the theoretical maximum performance. The theoretical maximum performance for this program is something you have to know how to analyze if you want to do actual optimization, the number one on that list. The theoretical maximum for this terminal program is bounded by several things. You need to know what each of those things are, but because, I've been around the block a few times, I didn't really have to do all of that work to know what it would be. I knew it would be this, right? Now, normally what you'd have to do is you have to go, okay, how big's the pipe to the graphics card? How fast is it to check out, these sorts of things, whatever. I knew that this would be my theoretical maximum, right? Because all of this stuff costs, and there's no way it was going to go faster than, say, the pipe to the graphics card for what I needed, right? So I knew this was going to be it. But even if you didn't, you could have figured that out. So when we actually talk about the optimization part, that arrow there, the speed over which the bytes can be sent through this, which requires them being sent all the way through here, is going to be the thing that we need to figure out. So we need to do some testing to figure out how fast it can go. And then that will be our benchmark against which we are trying to optimize, because we're trying to get up to that level. Okay. So let's talk about how the terminal part works now. I'm going to erase this diagram because you don't really need it for anything now that you understand, hopefully, what's going on here. In this giant unnecessary part of the system, you should be aware of effectively all of this can be boiled down to just this arrow. Some bytes are coming into the terminal. The fact that they're coming in much slower than they should is because of this, but we know we can't change it, so that's just where we're at. Now, how does non-pessimized coding work? I said I pretty much always do the number 2 bullet point in that list, which is non-pessimization. What's the mentality? The mentality is actually extremely simple. It is, what is the minimum amount of work that you're asking me to do? Type that in as close as you can, right? That's what it is. Now, normally, it's a lot easier than it is in Refterm. Refterm is actually a very hard program for the number 2 non-pessimization criteria, for the reason that I am required to use someone else's code in order to make it work. I knew I didn't have very long, and the original version of the Refterm was actually done in 3 days. It was even less than that, right? The very first version that I did. So in that amount of time, I know that I need to use Windows' standard Unicode parsing and glyph generation. I know that I need to use that. So I'm starting off actually with Refterm on a bad foot. I don't actually have the ability to apply the non-pessimization standard because I've been dumped a giant pessimized thing in my lap that I don't have a choice about using. This didn't bother me that much because part of the point of doing Refterm was also to show that even in the circumstance where you're dealt a bad hand, which is what people normally encounter when they're programming. They're in an organization they can't change, they have to use particular libraries, they're using a legacy code base. You don't want to just throw up your hands and say, well, I'm going to continue to produce bad stuff. You don't have to. You can work around these things, and so that was actually something that I didn't mind when I was doing Refterm, because I thought that was part of the point. It makes sense to me that I should have to deal with some really nasty, poorly designed, slow-functioning, ugly API, probably buggy, thing that just gets dumped in my lap. And those two things were direct write and Unicode Uniscribe, I think is what they call it, right? And what these are is they're just ways in which you call the operating system to do things like figure out which glyphs you're going to need for a UTF-8 stream, and then to produce those glyphs as little like pixels, that you can eventually draw onto the screen. So the very first step that I know in my head is going to happen before I ever type in any of this code, right, is you need to put a hard division between your code and the code that you know is not good, and then you have to find ways to cache around it. So you need to find ways to take the output of that code and reuse it without ever re-entering the code again. So I knew before I ever did anything on this code base that it was going to look something like this. Uniscribe, direct write, over here, right? My code over here, so this is Microsoft, and this is me, right? I knew there was going to be something here that acted as a cache to isolate me from this side of the code. So there was going to be some kind of two-directional flow where I call the lousy code in the system and have it do something. I take the answer and I cache it so that I minimize the number of times I call the bad code, right? For when it's you and Microsoft, you can just assume that this is the bad code over here, and then your responsibility is to write the good version, right? So you're trying to isolate this onto the other side. Okay, so we know there's going to be a cache in here that prevents us from having to talk to this very often. So I knew the code would look like this. Furthermore, I knew that there was nothing I could do about that input side, the pipe that was coming in. I knew that was going to be a big deal, that input pipe side of things. So what you want to do there, because it can't be fixed and it can't be cached because you're not asking for things, it's just a pipe that's coming in. I knew that I wanted to minimize the number of times I had to do anything to what was coming in. When something comes in, I don't want to do a lot of operation on it, right? I want it to stay as simple and as minimal, as hands-off as possible for the pipe that comes in. So I knew that the pipe that comes in here from whatever the kernel or command exe or whatever you want to have your flow look like, the final output of it that you want to feed into the terminal, I knew that this needed to go into some buffer, right? Because I have to call the kernel to get it. But when it comes into this buffer, I need to never touch it, right? I need to never move it. I don't want to massage it, change it, nothing. I want it to go into this buffer, and then the entire thing should work on top of the buffer without ever touching it. Now, what do I mean by that? Well, if you look at the kind of code, if you look at the code that's in Windows Terminal, for example, which is where this whole thing started, you will note that when data comes in, they do all kinds of things with it. It goes through string classes and allocations and reshuffling and all this stuff. All of that just is work the CPU didn't need to do. The bytes are the bytes. I don't need to put it in a string class. I don't need to allocate memory for it. I don't need to shuffle it around. Just whatever the buffer is that I call the kernel and say, put the bytes in here, I should be able to do everything just by looking at that buffer, right? So this is the start of my thinking of this system, is everything that talks to Microsoft should be cached to avoid it contaminating the code base with bad performance. And everything that comes in off of the pipe should go through as little touching as possible. Read it when you need to, never write, and never move, reorder, or copy, because each of those operations is unnecessary. A terminal just displays things on the screen. It doesn't edit anything except for the little command line part that you're typing, right? So there's no reason why I should ever have to do anything with these bytes that come in. And that's crucial, because if I want to hit high bandwidth, if I want this thing to be fast, I can't be spending all this time as the bytes come in shuffling them around again. I will double, triple, quadruple, who knows how bad, the amount of work necessary to actually get this in here. 1x the work is I ask the kernel, it puts it in there. 2x the work is if I then have to copy those out into my own structures or something, right? So I'll make the thing half as fast just by by refusing to just leave things put. Okay, so we have the cache and the buffer here, and then it's just a question of what does it look like on top of this? Well, we know that a terminal is just a giant thing of cells, right? It's like something, to a first approximation, that's just like a little grid, right? And each one of the little pieces in the grid is some glyph, right? It's something. It's the letter A or the number 2 or whatever. And all a terminal is responsible for doing is taking this buffer, the things that came in off the kernel, putting them into their correct slots in here, and whenever new data arrives, or the user like moves a scroll bar or hits page up or something, right, to look at a different place in the buffer. So when new data comes in, we would probably move down, right, and look at the new information. When the user like scrolls up, we move back up in the buffer to look at older information. And at some point, we will hit the end of the buffer. And in general, what happens in terminals is it doesn't just stop, and it doesn't just clear. What it does is it sort of like it evicts stuff that was in the beginning of the buffer. And so the oldest pieces of information go away, and the new pieces of information come in. So it's kind of rolling, right? So given these two things, I need to produce this, and I need to be able to produce this grid, right, on the screen with the knowledge that I may change which part of the buffer I'm looking at. Now, going into this, I knew in Refterm that there would be like lots and lots and lots of excuses made for why it was fast. Meaning when people looked and they said, oh, the performance of Refterm was very fast and the performance of, whatever else is slow, the reason for that is not just because the person who wrote Refterm didn't pessimize all the code, which is the actual reason why it's fast, but they'd be like, it's because that code base doesn't handle blah, where blah is a random thing they picked without testing, such as scroll back or hyperlink underlining or something like this, right? So I wanted to make sure I handled the kind of most obvious ones of those that I could think of, and those were like line wrapping and scroll back. So I assumed that while I was doing this, I should have a good way of handling the fact that when a line wraps, it comes around to the other end, but if you were to resize the window, it would reflow the line. Because I knew that's the kind of thing people would randomly say was the reason it was slow, despite never actually testing to see if that was the case. So I wanted to make sure that was already in there. And the same with scroll back, right? So let's talk about this sort of, I don't know what you want to call this sort of flow, how this is actually going to go. The first thing I did was I said, since this is a scroll back style buffer, where new data evicts old data, that to me immediately just says circular buffer. I already said I don't want to do extra work when data comes into the buffer. So I want this to be a circular buffer where when I write data in, it just overwrites old data that I may have had, right? So what I did is I just took in memory, right? I said, in memory, this thing is going to be mapped 3 times. There's going to be a buffer in the middle, right? And I'm going to map the same buffer. I'm just going to repeat it here and here in memory. So that when I'm doing stuff, when I write into here, let's say that chunk, it also writes here and here, right? Imagine like the actual structure of this is such that it doesn't have to write there. It's just mapped, so it just shows up here and here, right? And if I, read over the end of this buffer here, I just get the beginning of the buffer again, right? Now, when I first started typing in Refterm, I thought I would probably have to do that manually. I'd have to make the circular buffer so that it would do double reads and double writes when it was near the end and that sort of stuff. But it turned out, and I thank Martin's Mosaico for pointing this out, because I didn't even know they'd added this. In the middle of Windows 10, the kernel actually added, finally, the ability to do circular mappings like this in the page tables without having to rely on basically Russian roulette, without having to rely on maybe you get it, maybe you don't style allocations, which was the only way to do it previously. And the reason that I don't use circular buffer mappings that often in, for example, code that I would, well, in fact, I never use them in codes I would ship to a consumer on older version of Windows, because you can't guarantee that you'll get this mapping. On Windows 10, at some point, you can. So maybe I should revise this statement, by the way. This is for everything above the kernel. The Microsoft kernel people are actually pretty good. Anyway, so looking at this particular piece of code, right? All this does to do the entire circular buffer start thing is it just maps the buffer 3 times. That's it. And then it never does anything else. So it never has to do double reads, it never has to do double writes, so it's maximally efficient because all that happens is as the kernel writes in here, I just change where the places that it's writing, and that's it. The same is true for reading from the buffer. I don't ever have to think about that circular buffer part because wherever I am, it'll just read it properly. So this is just an example of Windows 10 happening to have a nice feature in the kernel that they added, so you can do this reliably. The hardware was always able to do it for quite some time, but it was just not exposed through the operating system in a way that you could actually use it. But now it is. So I do it that way, and I have a fallback path that will work on like Windows 7 and that sort of stuff, but it's not 100% reliable, right? So that's why I say the new thing is a pretty it's a pretty nice improvement, because being able to use circular buffers reliably is a huge deal, right? It's really, really good. So that takes care of that. So now we know that we will literally be able to, anytime bytes come in, we can just romp them down in this buffer and we're done. We never have to worry about it. We never do any work. We never do any copies. There are no copies in the entire thing for this, where you're processing the data that comes in. It literally is just the call to the kernel that says, get the stuff. It romps into the buffer, and that's the end of it. Everything else works entirely out of the buffer, 0 copies. So again, that was really easy, right? This is like super easy. So easy. It's like 20 lines of code or something, and it's done. So that was really nice because I didn't have to really spend any time on it. I thought it was going to be nasty and I was going to have to write a bunch of circular buffer logic, but it turned out that the Microsoft giveth and the Microsoft taketh away. It turned out that the Windows kernel team gave me a present where I could start to use this very reliably for anything that ships on Windows 10, which is the only thing that Windows Terminal ships on anyway. So it's pretty nice. It's a pretty nice time-saving feature. So the buffer part is pretty much something that takes care of itself, right? There's nothing to it. We don't even need to talk about it because that's all that happens. It's pretty much a problem that solves itself, right? So we can stop talking about this for now, almost entirely. It's basically 0 lines of code. It's so simple, right? So that's great. But we still have this problem of how do we actually put things up to the grid, right? What do we actually do to figure out which glyphs go in which slots and then put them on the slots? So this is where the actual discussion started was just, talking about how these renderers might work. The renderer part's not actually that interesting. I can explain how it works, but it's really just not that interesting. It's something that people have done forever, and it is in fact just the same way that terminals were rendered in 1970, right? It's just if you go back to how actual terminals were rendered, they are rendered in exactly the way that they are rendered in Refterm. So not only is the renderer part of Refterm not advanced, complicated, or even interesting, it's actually ancient. The renderer in Refterm is exactly how a monochrome terminal display in 1970 would have worked. And that is that there is a shader in the GPU, right, that all it does is for every cell in the grid, it just looks into a piece of data to see what that cell should contain, which glyph it should contain. Then it looks up into a glyph table to get that glyph. That's it. That's exactly how that shader is literally just an emulator for the actual thing that a monochrome terminal had in its actual logic baked into it in 1970. So there's no modern tech at all. It's basically the equivalent of writing to B0000 or whatever in the old days of IBM 86s, right? That's all it is. So there was literally no optimization done on the renderer at all. It started with some code that Martin's Mosaico posted that he wrote immediately after this sort of thing started to show like, hey, this is really easy. And I modified it slightly. There was one or two things in it that I did slightly differently. And then I added some support for things like effects, like blinking, underline, etc. And again, this was literally just emulating the exact same things that old terminals used to do. Now, it's worth noting that there is some interesting stuff here to think about in terms of optimization that you could carry forward into future problems. This is an embarrassingly simple problem that didn't involve any optimization or work or timing or anything. But there are non-simple problems that have this kind of concept at their core. And the concept is whether or not the renderer goes forwards or backwards, right? Another way to say is it implicit or explicit how the renderer goes? And what I mean by that is, in one kind of renderer, which is the traditional kind that was more common 10 years ago, the kind of rendering you're doing is you take a bunch of like little triangles or squares and you feed them forward through a system to find out where they go on the screen, and then you generate the pixels on the screen by iterating over the ones that are touched by that triangle, right? This is a standard forward renderer. It's an explicit renderer. An implicit renderer or backwards renderer is one that does the opposite. It starts with pixels on the screen and then it looks up into a data structure to find out what should be there. Backwards renderers are always have the potential to be drastically more efficient than forwards renderers, but to the extent that GPUs have specific code in them for the forwards rendering, like the rasterizers and triangle processors and all that sort of stuff, sometimes they're not. But in the case of something like a terminal, where it literally can almost for free do the lookup to find out what should be on that pixel, it's the obvious choice, right? But for systems that are more complicated, it may not be the obvious choice. It depends. But understanding the difference between forward and backward in that way, between feeding things down a pipe, figuring out which pixels they touch, and rasterizing the pixels, there's a difference between that and iterating over the pixels and seeing which primitives should be on them. At some level, they converge to the same thing because at the very bottom, you're always iterating over a block of like at least 4x4 pixels, because even rasterizers, by the time they get to blocks of like 4x4, they run implicitly. And the reason for that is because they're wide instruction units and that's just more efficient and blah, blah, blah. But the point is understanding the difference of how you determine which primitives are involved in an operation, being forwards or backwards, well, it makes a difference, right? So in a sense, the fact that this is an embarrassingly easy problem does mean that I didn't have to do that thinking. I just knew that a backwards renderer would be fine, so I just did it. But if you were really in a situation where you didn't know, like let's say that there was a lot of like off-center stuff happening where the grid squares weren't all perfectly aligned and there were many planes of text involved and some of them were opaque. once you add enough complexity to the system, it may be that a backwards renderer isn't so smart anymore. Maybe it is, maybe it's not. And at that point, if you wanted to do actual optimization, you would need to look. And you'd actually need to go time things and see which one was better and which one was worse. Again, almost no optimization on Refterm. This was all just non-pessimization. So all I was doing is say, what's the simplest possible shader I can write? Well, it's got to fill each pixel. It's got to fill the pixel with the glyph that goes in that pixel. I know it's a grid, so I'm just going to have a grid. It looks in the grid. That's the glyph, and you're done, right? So that's why that works that way. Not because it was optimal, or not because I spent any time figuring out how to run it, but because it was the simplest thing to write, and I knew it didn't add much extra work for anyone to do, whether it's CPU or GPU. So it was just a nice, easy way to ensure that that wouldn't be a bottleneck on the performance of the terminal. So now let's get to the final piece of the puzzle, which is how do we determine what that grid is, and how do we generate the glyphs that need to go in that grid? That's the end of part 2. When part 3 is available, the link will be in the description below. And of course, the link to our Kickstarter is also in the description below, so please check that out if you get a chance. I'll be back here tomorrow to post part 3, where I'll go over how data flows from the circular buffer up through the parsing into actually displaying it on the screen. So hope to see you back here for that. Until then, please check out the Kickstarter, and we will see you on the internet.